Okay, so we are going to look at our sugars and then trying to identify the characters of each sugar molecules. We shall begin with the easiest one, the albutin, which is the first one actually. Albutin is a kind of drug and we use it for some kind of medicinal purpose. But anyway, the albutin is sugar derivatives, as you can see. So first of all, what you have to do is to find the number of carbon in the molecule. So the number of carbon in the molecule of albutin is here, 1, 2, 3, 4, 5 and 6. The right hand side is the nucleophile that reacts with the sugar and then creating this kind of glycoside. Okay, so this is the nucleophile, and then if you have to find the glycosidic carbon, the glycosidic carbon is the carbon that is bound to two oxygen atoms, right, like this. So that means this is the glycosidic carbon, and then if we cut this out, we return it back to the open chain structure. But unfortunately, because we don't have hydrogen atom here, this molecule is substituted with the hydroxy group of the glycosidic position. So this is a glycoside already. So this one cannot be opened by the equilibrium, right? So this is negative to the Benedict test. Okay, so if you look at our glycosidic carbon, let's say that once this is OH, right, and this is a carbonyl group. So the carbonyl was attached with the carbon here, and another chemical bonding is hydrogen atom. So previously, this is the carbonyl group with R and H on each side. So this is the aldose sugar, right? So this molecule is called aldol, and because of six carbon atom in the molecule, so we call this as aldohexose. And the albutin is negative to the Benedict test. Next one is the sucrose. Okay. Sucrose is a disaccharide, similar to the cellobiose over here. Cellobiose is composed of two molecules of glucose attached together. But now for sucrose, it's composed of left-hand side here is glucose and right-hand side is the fructose. So how can we know that? If you count the number of carbon atom in the left-hand ring, it is 1, 2, 3, 4, 5, 6. So left hand is hexose sugar. Again, you have to find the glycosidic carbon or the carbon which was appeared as the carbonyl group. And the glycosidic carbon now locked with two oxygen atoms. Okay, so this is the glycosidic carbon. One of the chemical bonding is attached with carbon atom in the ring, and the other is hydrogen atom over here. So as you can see, this is aldehyde group. So this is aldohexose again. Now, on the right hand side, we have another sugar molecule containing 1, 2, 3, 4, 5 and 6 carbon atom. So this is hexose again. Now, we have to find the glycosidic carbon atom which is attached with two oxygen atoms. So the glycosidic carbon atom is on your left hand side. And if you look at this glycosidic carbon, this carbon attached with carbon and also another carbon atom over here. So your carbon atom, the glycosidic carbon atom attached with carbon atom in both sides. So this is ketone, character of the ketone. That means this right hand ring is formed from the ketose sugar. And we can call this as ketohexose sugar because it is the ketose sugar composed of 6 carbon atoms in one molecule. So aldohexose and ketohexose, they lock together with this oxygen atom. And if you look at your glycosidic carbon, if the glycosidic carbon attached with OH, then the OH can be deprotonated and turned back to carbonyl group. But this is not the OH, this is OR. So this whole group here is act as a nucleophile attached with your first sugar molecules on the left hand, right? So this ring cannot be opened anymore. So this ring is negative to the Benedict test. And the right hand ring, if you look at the glycosidic carbon over here, we lack of OH again, because the hydrogen atom is not here, so it cannot be deprotonated and turned back to your original form of ketone. So this is also negative for the Benedict test. So this is why your sucrose or the table sugar is not reacts with the Benedict. This is because both of the ring was locked completely with glycosidic bond. So you cannot open it out to be carbonyl group. So it's inert to the Benedict test. Unlike the other one over here, cellobiose, okay, which I was described already, this is still active with the Benedict test because the left hand ring, even though the left hand ring was locked, but the right hand ring is still opened, right? So in equilibrium, this one can be open or closed, right? So in the open chain structure like this, the aldehyde group will react with the Benedict test. So after this one was reacted, then the closed conformation, the closed ring structure open out by the Le Chatelier principle. So at the end, the whole molecules, okay, on the right hand side actually, the right hand part can react with the Benedict test. So that we can say that this sugar is active with the Benedict or positive with the Benedict. So this is the reducing sugar, but this is non-reducing sugar. That's it. Now from monosaccharide, disaccharide, we are going to look at a trisaccharide. So in this trisaccharide, we have 3 rings. Okay, the first ring composed of 1, 2, 3, 4, 5, 6. Again, 6 carbon atom as hexose sugar, and this is your glycosidic carbon, okay, composed of 2 oxygen atom. Okay, so this is formally present as the carbonyl group, and your carbonyl group over here linked with 1 carbon atom, and the other is hydrogen atom. So both sides of your carbonyl group, one side is carbon, the other is hydrogen, so this is called aldehyde. That means this molecule on the left hand is your aldohexose. Now we come to the second structure, second ring in the middle. So again, count the number of carbon in the whole molecule, 1, 2, 3, 4, 5, and 6. So you have 6 carbon atom. Again, so this is your hexose sugar. Okay. And if you count the number of, and if you look at carbon, looking for the glycosidic carbon, what you can see is this one, because this carbon connects with 2 hydrogen atoms, right? So this is glycosidic carbon. So you can, if you cleave the ring, if you can possibly cleave the ring, you can see that your glycosidic carbon over here or the carbonyl group connect with 2 carbon on both sides. So that means this is ketone, and this is called ketohexose sugar. Now come to the last ring on the right hand. Number of carbon over here, 1, 2, 3, 4, 5, and 6. Hexose sugar again. Okay. And if you look at your glycosidic carbon, or the carbon connecting with 2 oxygen atoms, so this is your glycosidic carbon. Okay. Your glycosidic carbon attached with carbon here, and obviously the other one is hydrogen atom. So this is previously formed as aldehyde, and this is aldohexose sugar. Oops, sorry. So the last ring here, number 3, is aldohexose. So you have aldohexose, ketohexose, and aldohexose connected together. And where's the glycosidic bond? Again, so if you look at this glycosidic carbon, right? So this is your glycosidic bond labeled in black over here. And because you lack of glycosidic OH, so if your oxygen here has no hydrogen atom attached with it, then it cannot be deprotonated and turn back to the carbonyl group anymore. So this is negative to the Benedict test. On the middle ring here, as you can see, we have glycosidic carbon connecting with, instead of OH, you have OR. Okay? Because OR is very stable, you cannot just cleave the OR out. You can cleave only OH by dissociation, right? Deprotonation. So you cannot cleave the OR and forming the carbonyl back in the system. So that means it's locked completely. And because the ring cannot be opened, then it's negative to the Benedict test. Now last ring on the right hand, the glycosidic carbon is over here, and you have no OH left. This is OR again. So you cannot deprotonate the hydrogen atom of OH, right? So you cannot turn it back to carbonyl group. So this is again negative to the Benedict test. Okay, no? So that the myelocytose sugar. Now we come to the last one, which is quite a bit complex structure of monosaccharide. This is a special type of saccharide, as I said. The saccharide does not really happens only CHO in the ratio of 2:1 for H and O. Sometimes you have this kind of thing. You have nitrogen atom in the whole structure here as well. And you have not only OH group, you also have amide, you also have carboxylic acid. This molecule is called sialic acid. This is a kind of derivative of sugar, of monosaccharide. Now, if we have to look at the structure, first of all, we have to count the number of carbon atoms first. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, 9 carbon atoms. So this is 9, right? The word 9 is nona. So this is nonose. Okay. Because if you have 3 carbon, it's triose, right? And then tetrose, pentose, hexose, heptose, octose, and nonose. So this is nonose. 9, nona is 9. And for the glycosidic carbon, the carbon together with 2 hydrogen atom over here. So as you can see, this is glycosidic carbon connecting with carbon and carbon in both sides of the carbonyl. So this is the ketose sugar. So this is ketononose. Okay. And if you look at this glycosidic carbon, it is attached with O and H. So OH here can deprotonate it, right? And return the carbonyl group back to your system and cleave this out. So if it can go back to the original ketone, right? Normally original ketone over here should undergo oxidation by Benedict test. But if you go back and look at the reaction of the ketone, the Benedict test can oxidize the alpha hydroxy group of the ketone to be diketone like this. Okay? But as you can see, if you go back to the ketone, this is not, this carbon has no OH. So there is nothing to be oxidized. So this sialic acid is still negative, still negative to the Benedict test, even though the ring can open out. Okay? Because you have no such kind of chemical functionalities. Okay? The thing that Benedict test can oxidize is only alpha hydroxy ketone and also the aldehyde. the aldehyde will undergo oxidation, and you have the carboxylate ion acid product because the reaction is occurring in the basic condition. So over here, if you go back to the double bond here, carbonyl group, there is no OH nearby, right? So there's no chance for the oxidation. This is sialic acid. Okay, I not count the number of carbon over here, 2 carbon over here, because this is actually coming from acetate group. Okay, and then acetylation on this NH2. So previously this is NH2 amino group, but this amino group was acetylate with the acetic acid by maybe acetyl coenzyme, anything like that. So this is ketononose. Okay, so roughly this is all about the character of the molecules of carboxylic acid and physical properties and also chemical properties, which is reflected by the functionalities, the structure of the molecule. Okay, so I think we shall end the carbohydrate over here, and then we continue with the next functional group, with the next type of biomolecules. Okay, but anyway, it is based upon the carbohydrate because the structure of the next type is still have a core. The core structure is constructed out of the carbohydrate, and then you will see what is it. Okay, go to the next biomolecules.